Hi, this time we dive deeper into the physics engine. So some more advanced things, very nice thing like a cloth, so you can make cloth, or a flag, a waving flag with the physics animation. And we can add joints and motors to objects. Let's start with the cloth. So what we can do in Unity to any object, we can add a so-called cloth component. And then what will happen is that the polygons of that object, they will be able to move with respect to each other. So if you have a fixed mesh, let's say here with two polygons, then usually these polygons are fixed with respect to each other. They can't move. Only the whole thing can move, but not the polygons separately. But if we have a cloth, then the polygons will be able to bend like this with respect to each other. So then, yeah, that is part of the cloth behavior. The bending of polygons with respect to each other will be possible, and also polygons will be able to stretch. I cannot show that here. This is a fixed physical thing. But with these cloth polygons, they can be stretched, so they can be made longer or shorter. Depends on how the cloth is supposed to behave. The physics engine will make calculations how to bend and stretch polygons such that it acts like a cloth. So with this, we can we still have the mesh, but the separate polygons of the mesh, they move. They're still connected to each other, so it's not like a particle system where every polygon moves on its own. The polygons, they stay connected, but they can bend and they can stretch, and in that way it can behave like a cloth. And in order to do that a little bit realistically, we'll see it's not always that realistic. We can specify per vertex how much it is allowed to move from its original position, and also we can specify how much it is allowed to go inside its original mesh. So against the normal, and normal is pointing outward, how much can the vertex move inside the mesh, and we can specify how much a cloth can collide with itself. I'll show you what is meant by that. So as I mentioned, we can start with any game object we want. Let's start with a plane, for example, and we can turn that object into a cloth. So this plane, I could turn it into a flag. Let's first put it horizontal by rotating it around the x-axis, like this. And then how can I make a cloth out of this? Well, simple. I add from the physics section, I add a cloth component. Before I do that, watch the components that the plane has already. It has a mesh renderer, it has a mesh collider, and of course a mesh and a transform. If I add the cloth, you see that the cloth component is added, but you also see that the mesh renderer has now been replaced by a skinned mesh renderer, which you remember hopefully from the avatars. That is a kind of mesh renderer that allows the vertices to move. And that's what we need also here in this cloth. Well, if I do that, just that, it will fall down. As you see, the cloth, one of its values is that it can use gravity, so it will just fall down. It's a physics engine that adds gravity. If I switch that off, then you can already see a bit of the cloth behavior. But yeah, not enough to really see that. You can see here in the coordinates that things are moving, but it's not very clearly visible. So it's better to leave the gravity on. And then, yeah, like you would with a real cloth, you have to pin it up on the top. You have to take a few points where you fix the cloth, otherwise it will fall down to the floor. So we can do that here. We can add so-called constraints. And for example, I can do that for the 2 points in the corner. I can select them, and then I can say my brush is a bit big. And so for selecting, you see there is a brush, and you can also see, I'll go a bit closer. Every vertex is shown like a black dot, and when my brush is hitting it, it turns blue. So that means it's selected, and then I can do something with that vertex. But I want to do that with the vertices on top. So this one over here, I want to fix that one. So now the next distance that it is allowed to move is 0. So that point will stay always where it is. And I'm going to do the same with the point over here. Go close so we can see it's now red. So that means it's not allowed to move. The black points are allowed to move freely. The red points, they have a max distance of 0, as it is mentioned here. So now these 2 points, they will stay where they are. And then the rest of the polygons and the vertices can move. With gravity, let's just switch it on again. And then we get this behavior. If we wait a little bit, you can see that it's not a fixed plane anymore, but there is now some movement. And I can add a wind force, for example in Z direction, which blows the cloth forward or backward, positive or negative external acceleration. I can add an X force, which will try to blow it sideways a little bit. So now it's like a cloth hanging in the wind and moving because of the wind. As you see, it's quite simple to achieve this effect, and it's looking reasonably realistic. It's not perfect, it's an approximation, it's the best we can do, but I can also make some settings to make it look better. Just to show the effect if I constrain it only on one point. So I will switch this one off. So the next distance is then switched off. So then this point will fall down freely. And only the other point is fixed. And we get this. And yeah, you see it still behaves reasonably. The external acceleration is switched off again. It's an okay effect. It's an okay effect. It's not perfect, but it looks reasonable. We can do the same with any object, so I can also start with a sphere and give that a cloth. And the same happens, it gets a skinned mesh renderer. If I don't do anything, it will fall down like before, so I have to constrain at least one point here also. Let's use a smaller brush and constrain one point here at the top, which is now red, so it means it's constrained. And yeah, what you will see is that, let's put it a bit closer to the camera. what we see is that it deflates like a balloon. There's a hole in it. So also a nice effect. But what you see here, let's go in this view to see it even better. That is that the polygons, they seem to have gone through each other. So instead of hitting each other, they go through each other. And that's kind of intercollision, which we don't want. That's not realistic. But we can also switch that off. That is this button here, the self collision, self and intercollision. And like before, I can select vertices here. Wait, and then let's select them all. And then not allow a self collision. While I did that here, the self collision distance appeared. That was not there in the inspector before, but now we have self collision distance, which is currently set to 0. If I increase that, you can see that in each vertex that I selected, now a sphere is drawn, and that is as far as the vertices are now allowed to intersect. So if I make them a little bit overlapping, like this, that's maybe too much even, then we will see that the vertices will not go through each other anymore. But it will more look like it is supposed to look. Like there's still a little bit of air. It's not perfect. Here you see an area where it still does not look perfect. Maybe that's because that's because the back side of the sphere was not selected, so I have to select again and do the same here. The vertices on the back side of the sphere were not selected previously for intercollision. So now we have this effect, and if we now move around it, you see that it's okay now. The vertices do not have the so-called self-collision anymore. They don't go through each other, but it looks quite realistic in this way. We could have applied the same to the plane. Let's go back to the plane for a second. Give that a cross component. Put it in the 0, 0, 0. Rotate it vertical. What I could also have done is I constrained now the point on the left. I could also have constrained the point in the middle over here. And then you see the same intercollision effect that we don't want. Clearly visible here. The two parts of the cloth, they just go through each other as if there's nothing. That can be prevented also by specifying the intercollision. So you select points, you define self-collision and intercollision, and then you increase this distance such that the spheres hit. And then, we see it's moving much more realistically. If you look very closely, you see that it's still not 100% realistic. For example, because of the back face culling, as soon as we see the back side of the polygon, it becomes invisible. But it's reasonable. It's reasonable. So with these settings, by adding the constraints and the intercollision settings, and also here playing with the stiffness, with that you can you can change how that object behaves. I can increase the stiffness. It's much more stiff cloth than before. That's yeah, one of the settings you can play with. What I also have to show is that this cloth can collide with certain colliders. If you look in the cloth component, then you see here at the bottom that there is a list of capsule, sphere, and sphere colliders. No box colliders, but we have capsule and sphere colliders. It's a list, initially a list of 0, but I can make a list of 1. And then I can add one combination of 2 spheres that this cloth will collide with. So I'm just going to add a sphere. It can also be 1, doesn't have to be 2. I'm going to move it to 0, 0, 0, and move it a bit towards me, like this. And then I specifically have to add this sphere to the list of colliders. Drag it as the first collider. You can also add the second one, then we have a kind of capsule between the 2 spheres. We have a capsule that can be used as a collider. And with this sphere, I can move the cloth. Let's go to the scene view, select the sphere, and I'm going to move it backward now. As you see, when I hit the cloth, it moves the cloth. More backward. It's not perfect again because I did it probably too quickly. I went through the cloth and now it's behind. And if I bring it back, it's going to move the cloth towards me, but also again, if you do it too quickly, it's going to be through. Also depends on stiffness and other settings of the cloth itself. But with that, by defining a few colliders or one or more colliders, you can yeah, make the cloth move. The thing is, these cloths, they are basically meant to be used as clothes on an avatar, a humanoid avatar. So a cap over the head, for example, or a cape, which Superman has on his back. So then the head, the sphere that replaces the head, is supposed to be one collider, and then the cloth will be draped around it. But it's not supposed to move that much like I just did. The next thing about the physics engine I want to discuss are the joints, which basically has nothing to do with the cloth. The only resemblance is that it's both supported by the physics engine. So we are discussing advanced features of the physics engine today. Joints are meant to connect objects. We have connected objects before by creating parent-child relations. So that's one way of doing it. You can make an object a child of another object, and then it will always follow its parent, as we have seen before. Or you can have 2 objects that have the same invisible root parent. We've also seen that, which is often a better solution. What you could do is, in a script, you can just copy the transformation of one object into another one, and then that other one will follow the first one. That's also a way to connect objects in a script, but not done that often. But the third way is to create a joint. It's a part of the physics engine, so you have to use rigid bodies for that, which is not necessary in the parent-child, of course. But yeah, then these joints are quite powerful and nice. So with this, you can make wheels for a car, or you can make a door that's connected to a wall, or other connections between objects. Notice that this is not the same as the joints that I talked about in avatars. In avatars, I talked about humanoids, I talked about bones and joints between bones. the joints that I mentioned there are just transforms that are rotated. So that's a parent-child relation type of connecting objects. What we talk about today, these physics joints, that's really something else. And they are meant, it's part of the physics engine, they are meant to connect to objects in a flexible way. There's also a fixed joint, then they are connected and they cannot move with respect to each other. But most joints are flexible, so they can move around one or more axes. As I mentioned, wheels on a car, doors are connected to the wall, etc. We have different types of joints with different degrees of freedom. Basically these. So you have, if I start at the bottom at the hinge, you have joints that have one axis of rotation, 1 degree of freedom, like a hinge on a door or a wheel on a car that can rotate around one axis. When you are steering, you have 2 axes, but for movement, the wheel is rotating around one axis, so that's also a hinge joint. We also have the universal joint, which has 2 axes of rotation. So, yeah, like a drive shaft in a car, it can rotate left, right, up, down, but not twist. And the ball joint that can rotate in any direction. So it can also, the two bodies can also rotate like this between each other. And there are also joints that can not rotate but slide. That are linear joints that slide with respect to each other. And we have the fixed joint. So that are, let's say, the common joint types. So every joint has a certain position, which Unity calls the anchor point. That's the point that it rotates around, and then it has a number of axes of rotation, 3 or 2 or 1 rotation axis, and the slider has 1 translation axis, linear axis. A joint is a component. It's handled by the physics engine, so as I mentioned, we do need rigid bodies for that, and it's a component that you can add to a game object. If you add a joint, automatically a rigid body is also added. And a joint is added to one of the 2 objects. So you connect 2 objects with a joint, but the joint is added to one of the 2 as a component, and then the other one is the so-called connected body. So that's asymmetric. The joint is really a component of one of the 2, and the other object is a connected object. And then we have the anchor that defines the point around which the joint rotates. And yeah, as I will show in Unity, we also have the connected anchor. That's the same point, but seen from the point of view of the other object, the connected object. That's called the connected anchor. But basically, that's the same physical point, the same global point. Yeah, let me just show this in Unity, how simple it is. So I'm just going to put a cube over here. Let's put it in 0, 0, 0. Well, let's look at it from a lighted side. And then I'm going to add a hinge. It's about physics, so we have to look in the physics section. And here we have a hinge joint. Hinge is a joint that can rotate around one axis of rotation. It's now a component of the cube. Here we have the hinge joint. As you see, it has quite some attributes. And automatically also this rigid body has been added. In this case, there's no connected body yet. That means that the other side of the hinge is now connected to the world. So it will stay on a fixed point in the world. So this cube, although it has a rigid body and although it uses gravity, it will not fall down because it has a hinge, and the other side of the hinge is connected to the world, to the fixed point of the world. And that's the connected anchor. That's the point 0, 0, 0. We can see that anchor if we look Yeah, also from here you can see it a little bit, but if you look at it from the top, then here you see this very small arrow. You have to look carefully because it's really drawn very small, but that is the anchor point. So when I start running the application, you will see that the cube can rotate around this point and around this axis, so forward and backward. It can swing forward and backward around this point. It's easier to go to the scene view. So for now, it's just hanging there statically because there's nothing moving it. And also, if you look at the coordinates, there's nothing going on. But if I just give it a little movement by in the scene view directly, which can also be done in the script, then you can see it starts swinging around that axis of rotation, around that anchor. That's the anchor. And it will just swing, not continuously. It will, after a while, it will slow down, but there's almost no friction in this swinging. But that's very easy. In the same way, I can also connect it to another object. So let's add the sphere and move that a bit above the cube. And then let's connect the two. So I want to use the sphere as a connected body, which should be as simple as dragging and dropping. But as you can see, it cannot be used as a connected body for the simple reason that it does not have a rigid body yet. It's not in the physics, under control of the physics. So I have to give it a rigid body. To stop it from falling down, I also make it kinematic. And then I can use it as a connected body in the anchor. So now the two are connected. You don't really see that in the scene view, but now the two are connected. The sphere is the top of the hinge, and the cube is the bottom of the hinge. And yeah, they are connected through this hinge. So if I move the sphere, you will see that the cube starts swinging. So if I move the sphere forward and backward, you see the swinging of the cube. It's actually swinging a bit too much, as you see. There are collisions which are not handled well. If I move left and right, then it does not swing in that direction. It swings in the around the x-axis. So up and down, yeah, not of course. So this is the anchor point, and it's swinging around that point. And the sphere is now the connected body for the cube. So the sphere is connected body for the cube. Anchor point. And we can move the anchor point. I can put the anchor point higher. Then now the anchor is somewhere here, somewhere inside the sphere, or maybe even already above the sphere. And now the cube is rotating, swinging around that anchor point. I can also change the axis to 1, 0, for example. It's not a good idea to do that while the thing is in motion. I do that here. If I want it to swing in the around the, yeah, let's not do the y-axis, let's do the z-axis. Then it's now not moving in this direction anymore, but now it's moving and swinging in that direction. So yeah, that's easy. To make a hinge between two objects, that's very easy. What you can do, one of the things you can do is limit the rotation of an object by editing the angular limits. So by default, it can rotate in all 360 degrees. So theoretically, I could move it all around. But you can use limits, as we see here. And if you do that, then you can specify an area, and the cube will only be allowed to swing within these limits. So if I make them smaller, you can see it better. So if I now move the sphere, you see it only swings so far and not further, because I use limits, and the angular limits I defined how far it is supposed or allowed to swing. So for a door, for example, a door is only allowed to move that far. It's like a door stopper. So this is the hinge joint, basically quite simple. This connected anchor is not really something to worry about. It's simply the coordinate of the anchor seen from the point of view of the sphere. So from the center of the sphere, this anchor is on a y of minus 0.506. From the center of the sphere to the anchor is 0.506 if I move the sphere upward. And then back to the cube. You see it's not immediately updated, although I did specify auto configure connected anchor. But when I run it, then it's updated. So now it's 0.825. So from the center of the sphere to this anchor is 0.825. If we look at the position of the sphere, it's 1.325. So this is the point 1.325. The cube, the center of the cube is in 0, 0, 0. This anchor is in 0, 0.5, 0. 0, 0.5, 0. So the position of the anchor is 0, 0.5, 0. So from the center of the sphere down to the anchor, that's minus 0.825. Do the math. That's true. So that connected anchor position is auto configured at runtime. I don't think it's very useful to switch that off and use a different connected anchor, because they're supposed to be the same points. What about springs and motors? What we can do here is we can use a spring on this joint. So let me increase the angles a bit. Oh. And then I'm using a spring. So I'm increasing the spring force. And what will happen is that the target position also has to be increased a bit. That the cube, like with a spring force, it will be pushed to one side. It will not just hang exactly under the sphere, but because of the spring, it will be pushed a little bit to one side, depending on the force of the spring. So I probably have to increase it to see the effect, and let's also look at it from the side. And the target position, yeah, it's a combination. So no, I should look at it from this side, of course. But now by the spring, it's pushed to this target position, which is an angle. I had it too small in the beginning, and I now have a very high spring force. If I bring that back, then you'll see that now it starts falling back. So now the spring force is not enough, combined with the weight of the object, to push the cube to that target position. If I make the object lighter, that's very light, 0.5 for example, then the spring can push it a bit further. Then when the weight is back to 1, you see, then it falls a bit more down. So that's spring. It's like a real spring. It tries to push the cube to a certain target position that you specify. It's a spring, so like any spring, it does a few oscillations before it stabilizes. If you want it to stabilize faster, you can use the damper. So here we have a damper. If I switch the spring off and on again, and because of the damper, it doesn't have that many oscillations anymore. It's still pushing the object to the target position, but without that many oscillations. It depends on the size of the damper, how many oscillations you will get. Yeah, as you have seen, if it's very close to 0, then we have few oscillations. If it is 0, we have a lot. But the higher you put the damper force, the less oscillations you have. But the spring, that's a force like a real spring in real life that tries to push an object into a certain position. So use that if you want to do that. If you want to keep your object in this position as much as possible, because it's a spring, so if somebody pushes against it, then it will move. But for that purpose, use a spring. Next to the spring that I just showed you, we also have a motor force. So I already enabled it here. Use motor. The purpose of a motor force is different from a spring. With a spring, you want to get the joint into a certain target position, at a certain rotation. With a motor, you want to reach a target velocity, which means it has to make so many full rotations per second. So there's a different purpose. And in order to show the force of the motor, I did move the anchor. So originally it was in 0.50 up here. But that's difficult to make the cube rotate around that point because of the weight. It will take a lot of force to make full rotations. So that's why I'm moving the anchor to 0, 0, 0. That's the center of the cube. And I want it to rotate around that center by applying a motor force. So again, the difference between a spring and a motor is with a spring you can get the hanging object into a certain target position and it will stay there. And with a motor, you are going for a target velocity. So you are trying to make it rotate with a certain number of rotations per second. The velocity here I chose 7. So let's see what that does. And the anchor is now in the middle, so it will rotate around its center. Let's go back to the scene view. But I did not apply any force yet, so that's why it's not rotating. If I increase the force, you see it starts to rotate. Not full rotations because I still have the limits enabled. And, you should not do that if you want to make full rotations. So with this force, and now this cube is making the required number of rotations, which is 7. Well, not that many. If you want it to spin faster, you can increase the target velocity. I maybe increase the force a bit too much. I guess a bit less force is also enough to keep it rotating. And even 0. And once it is rotating, it will keep rotating, but it is not a target velocity anymore. So to get the target velocity, I should apply a bit of force again. It can be stopped. If I would apply a force to the cube, it will stop rotating. And how much force to apply for that to make it stop, that also depends on the force that I'm using here on the motor. The more force I apply here, the more force it will take to stop it from rotating. So we have spring and motor, and they have different purposes. Keep that in mind. The motor is to make full rotations continuously, like a wheel. The spring is to push it to a certain position and try to keep it there. And they both have force, spring force or motor force. Spring or force here. Spring has a damper to keep it from oscillating. And this motor has free spin, which you can enable to make it to disable the braking behavior, so then it will keep on spinning even if you don't apply the force anymore. So spring and motor, again, I repeat, they have different purposes. If you want to do something that is not requiring full rotations, then don't use the motor, use the spring. There are some other forces down here. Big force, for example, that is a force that is needed to break the spring, the joint. That's possible. You can destroy a joint if you apply enough force, and the brake force that you need for that's specified over here. So by default it's infinity, which means the joint will never break, but you can make that lower, and then the joint will break if you apply too much force. I also want to show you another type of joint. This is the hinge joint that we just saw. That's a joint that can rotate around one axis. But instead of the hinge joint, we can also, for example, use the spring joint. So let me add that to the cube, and then again use the sphere as a connected body. And what we get then is this effect, as the name says, it's a spring effect, like this. Nice. So it's moving up and down. If I move the sphere, the cube will follow as if it is connected by a spring. It will make all kinds of rotations. We can change some settings like the damper, which will again reduce the oscillations, the min and max distance, the tolerance, brake force again. And by the way, notice that in this case the anchor and the connected anchor are not in exactly the same space anymore. So for a spring joint, we see that this is the connected anchor, and this is the anchor itself. They are not in the same place anymore. For a hinge joint, they are in the same place because that's the place where they rotate around each other. But for a spring joint, the two anchors get separated. So the spring is actually between these 2 points. So the connected anchor here, the connected anchor here, and the anchor itself here. Between these 2 points, that's where the spring is working. So it is as if there is a spring or an elastic band between these 2 points. So that's why we have the connected anchor, because for a lot of types of joints, like the hinge joint and the fixed joint, they are in the same position, but for spring joints they can separate, and then the spring is between these 2 anchors. This is basically what we have as joints. So the hinge, the fixed joint, does not move at all. So that's really to connect to things in a fixed way, which is sometimes also useful. The spring I just showed, I'm not going to talk about the character joint, but the last type is the configurable joint. Let me quickly show that one. So remove not the rigid body, but the joint. And then add the configurable joint. And again, connect the sphere. Now I used configurable joint, and as you can see here, this one has really an overwhelming amount of attributes. That's because it can act like any type of joint. So if it's a configurable joint, you can configure it, as the name says, to have one axis of rotation, or to have two, or to have three. It can be a spring joint, it can be a linear joint, it can be anything. So this is very flexible. You can configure it to be whatever you want, but at the same time that also makes it quite difficult. So yeah, if I do this, if I run this, it's moving in any direction. I'm not even sure if there is a limit to how far it falls. No, even complete out of view yet. That's because the motion in y direction is free. There's no limit. It's also a linear joint, so it can fall in a linear way in any direction. I'm not going to talk about this too much because you probably don't want to use it. Let's stick to hinge joints and maybe a spring joint and a fixed joint for the moment. So this is really for advanced use.